Something happened out there in the darkness of space that no one saw coming. Not the scientists, not the engineers, not even the people who built the most powerful space telescope ever made. The James Webb Space Telescope looked out into the oldest corners of the universe and found something that should not exist. If this telescope had not detected it, no one on Earth would have believed it was real. The data came back from over 1 million miles away. Scientists opened the files, looked at the numbers, and thought their equipment had failed. They checked the telescope. They ran the tests again. Everything was working perfectly. The problem was not with the machine. The problem was with everything they thought they knew about how the universe works. For decades, we had a story about how the cosmos began and grew. We had a picture of how the first stars formed, how the first galaxies came together, and how long all of it took. That story made sense. It fit the evidence. It had been tested and confirmed over and over again. Then one telescope, floating in the cold emptiness of space, sent back a single observation that cracked the whole thing open. What did it see? How could one piece of data do so much damage to our understanding? And what does this mean for everything we thought we knew about the universe, the stars, and even our own place in all of it? To understand why this discovery matters so much, we need to go back to the beginning. Not the beginning of the universe, but the beginning of our attempt to understand it. For most of human history, we had no idea how big the cosmos really was. We looked up at the night sky and saw points of light. We gave them names, we told stories about them, but we did not know what they actually were. It was not until the early 1900s that we started to figure it out. A man named Edwin Hubble pointed a telescope at a fuzzy patch of light in the sky and realized it was not part of our own galaxy. It was a completely separate island of stars, millions of light years away. That discovery changed everything. Suddenly, the universe was not just big, it was unimaginably vast. But Hubble found something else too. He noticed that the light from these distant galaxies was shifted toward the red end of the spectrum. This meant they were moving away from us. The farther away a galaxy was, the faster it seemed to be speeding off into the distance. The universe was not standing still, it was expanding. If the universe is getting bigger now, that means it used to be smaller. If you wind the clock back far enough, everything that exists was once packed into a single point of unbelievable density and heat. That moment, the instant when everything exploded outward from nothing, is what we call the Big Bang. The Big Bang theory is not a guess. It is supported by multiple lines of evidence. We can see the afterglow of that explosion in the form of the cosmic microwave background radiation. This is a faint glow of light that fills all of space. It was released about 380,000 years after the Big Bang, when the universe cooled down enough for atoms to form. That light has been traveling through space ever since, stretching into longer and longer wavelengths as the universe expands. We can measure that light with extreme precision. We can map out tiny differences in temperature across the sky. Those differences tell us about the conditions of the early universe. They tell us how much matter was there, how fast things were moving, and how the first structures started to form. From all of this, we built a model, a detailed mathematical model that describes how the universe evolved from that first moment to now. This model is called the Lambda Cold Dark Matter Model, or Lambda CDM for short. It is the standard framework that cosmologists use to understand the universe. According to this model, the universe is about 13.8 billion years old. It started with the Big Bang, expanded rapidly, cooled down, and slowly formed the structures we see today. First, there was nothing but a hot soup of particles. Then atoms formed, then gas clouds, then the first stars ignited, then galaxies came together, slowly building up over hundreds of millions of years. The first galaxies were supposed to be small and messy. They were supposed to be clumps of stars just starting to organize themselves. Building a large, well-ordered galaxy takes time. You need gravity to pull things together. You need generations of stars to live and die, seeding space with heavier elements. You need merger after merger, where small galaxies combine into bigger ones. This process was supposed to take at least 1 billion years, maybe longer. The Lambda CDM model made predictions about what we should see when we look at the very early universe. It said we should find small, irregular blobs of stars. It said we should not find mature, massive galaxies until much later in cosmic history. And for a long time, we had no way to check. The early universe was simply too far away and too faint to observe clearly. Then came the James Webb Space Telescope. This machine was designed specifically to see what no other telescope could see. It was built to look at the oldest light in the universe and reveal what was happening in those first few 100 million years after the Big Bang. The Webb telescope is an engineering marvel. It has a primary mirror that is 6.5 meters across, made up of 18 hexagonal segments coated in gold. Gold is used because it reflects infrared light better than any other metal, and infrared is exactly what Webb was built to see. Why infrared? Because of that expansion we talked about earlier. When light travels across the universe, the expansion of space stretches its wavelength. Light that started out as visible or even ultraviolet light gets stretched into the infrared by the time it reaches us. This is called redshift. The oldest light in the universe has been redshifted so much that it can only be seen in the infrared. Previous telescopes were not good enough at seeing infrared light. They could catch glimpses, but they could not see clearly. The Hubble Space Telescope, for all its incredible achievements, was designed mainly for visible and ultraviolet light. It could see some infrared, but not the deep infrared where the oldest signals hide. The James Webb Space Telescope changed everything. It can see infrared light with incredible detail. Its instruments are cooled to temperatures colder than anything on Earth, just a few degrees above absolute zero. This is necessary because infrared light is essentially heat radiation. If the telescope itself were warm, it would glow with infrared light and blind its own sensors. By cooling everything down to unbelievably cold temperatures, Webb can pick out the faint infrared signals from the edge of the observable universe. Webb does not orbit Earth like Hubble does. It sits at a point in space called the second Lagrange point, or L2. This is a special location about 1.5 million kilometers from Earth, on the side opposite the Sun. At this point, the gravitational pulls of the Earth and Sun combine in just the right way to let an object orbit the Sun while staying in the same position relative to Earth. This keeps Webb in a stable spot where it can always point away from the Sun, Earth, and Moon, shielding its sensitive instruments from their heat and light. The telescope has a massive sun shield about the size of a tennis court. This shield has 5 layers of material, each one blocking heat from the Sun. The side facing the Sun can reach temperatures over 80 degrees Celsius. The side facing away, where the mirrors and instruments are, stays at around minus 230 degrees Celsius. This incredible temperature difference, all within a single machine floating in space, is what allows Webb to see the invisible light from the dawn of time. When Webb finally opened its eyes and started taking data, scientists around the world held their breath. The first images were released to the public in July of 2022. They were beautiful, deep fields showing thousands of galaxies, nebulae with swirling clouds of gas and dust, distant stars surrounded by disks of material where planets might be forming. It was everything we had hoped for and more, but hidden in that first batch of data was something troubling, something that did not make sense. Scientists started finding galaxies that looked too big, too bright, and too well-formed for where they appeared in cosmic history. Remember, when we look at distant objects in space, we are looking back in time. Light takes time to travel. A galaxy that is 13 billion light years away means the light we see left that galaxy 13 billion years ago. We are seeing it as it was in the distant past when the universe was still young. The standard model said that when we look at that era, we should see small, chaotic, newborn galaxies. But that is not what Webb found. Instead, it found galaxies that looked almost like our own Milky Way. Massive spiral structures with billions of stars. Fully formed, well-organized, impossibly mature. These galaxies existed when the universe was only a few 100 million years old. That is not enough time. According to everything we thought we knew, there simply had not been enough time since the Big Bang for gravity to pull together that much matter for that many stars to form, for spiral arms to develop. It was like finding a fully grown adult in a hospital nursery. It should not be there. At first, scientists wondered if they had made a mistake. Maybe the measurements were wrong. Maybe the red shifts were not what they seemed. Maybe there was something about the data that was throwing off the calculations. So they checked. They checked everything. They looked at the telescope's calibration. They looked at the instruments. They ran the numbers again and again. The results held. The observations were real. These impossible galaxies actually existed. One of the first objects to cause this confusion was given the name JWST 13-0. This galaxy appears to us as it was about 320 million years after the Big Bang. That is extremely early in cosmic history. At that time, the universe was only about 2% of its current age. And yet there it was, a fully formed galaxy with billions of stars. The discovery sent shockwaves through the astronomical community. Paper after paper was published, each one trying to make sense of what Webb had found. Some scientists proposed that our understanding of the early universe was simply incomplete. Maybe stars formed faster back then than we thought. Maybe the first generation of stars, the massive ones that formed from pure hydrogen and helium, were different in ways we did not expect. Others wondered if dark matter played a role. Dark matter is the invisible stuff that makes up most of the mass in the universe. We cannot see it directly, but we know it is there because of its gravitational effects. Maybe dark matter in the early universe helped pull things together faster than our models predicted. Still others raised an even more radical possibility. What if the lambda CDM model itself was wrong? What if the basic framework we had been using for decades needed to be fundamentally revised? This is not a question scientists take lightly. The lambda CDM model has been incredibly successful. It explains so many observations, from the cosmic microwave background to the distribution of galaxies to the abundance of light elements like hydrogen and helium. Throwing it out would mean starting over from scratch. But science is about following the evidence, even when it leads somewhere uncomfortable. As more data came in from Webb, the situation only got more confusing. The impossible galaxies were not a fluke. They kept appearing. Everywhere Webb looked, it found more of them. The early universe was not the dark, quiet place we expected. It was already full of light, full of massive galaxies that had no business being there. One study looked at a batch of 6 galaxies observed by Webb that appeared to exist between 200 and 700 million years after the Big Bang. These galaxies were shockingly massive. Some of them contained as many stars as the Milky Way does today. That should be impossible. The Milky Way took over 13 billion years to reach its current size. These galaxies seem to have done it in a tiny fraction of that time. The researchers who published that study were careful to note that their findings were preliminary. They pointed out that more observations were needed. They acknowledged that there could be sources of error they had not accounted for. But even with all those caveats, the basic message was clear. Something strange was going on. Let me give you a sense of the scale we are talking about here. The universe is currently about 13.8 billion years old. The galaxies Webb was finding appeared to exist when the universe was only a few 100 million years old. That means these galaxies formed in less than 5% of the time the universe has been around. To put it another way, imagine the entire history of the universe compressed into a single year. The Big Bang happens at midnight on January 1st. The cosmic microwave background is released a few hours later. The first stars ignite sometime in January. And according to our old models, the first big galaxies should not appear until at least spring, maybe summer. What Webb found was the equivalent of finding fully grown cities with skyscrapers and highways by the second week of January. The timeline just does not work. So what do we do with this information? How do scientists respond when their models are challenged by observations they cannot explain? The first step is always to make sure the observations are correct. As I mentioned, scientists checked the Webb data exhaustively. They looked for any possible source of error. They considered whether the redshifts might be misidentified. They asked whether there might be dust or other contamination affecting the measurements. Each time, the data held up. The second step is to see if the existing models can be stretched or modified to accommodate the new data. Maybe we do not need to throw out lambda CDM entirely. Maybe we just need to tweak some parameters. Maybe there is something about the physics of early star formation that we did not understand. This is where things get interesting. To explain the Webb observations, some scientists have proposed that the first stars might have been much more massive than we thought. In the early universe, before any heavy elements had been created, stars formed from clouds of pure hydrogen and helium. Without heavy elements to help the gas cool down and fragment, these primordial stars might have been monsters. Hundreds of times the mass of our sun. maybe thousands of times. Such massive stars would burn incredibly hot and bright. They would live fast and die young, exploding as supernovae and seeding space with heavier elements. If the first generation of stars was dominated by these behemoths, it might explain how so much mass could have been assembled into galaxies so quickly. But this explanation has its own problems. Even if the first stars were more massive than we thought, there is still a limit to how fast gravity can pull matter together. The universe in those early times was still very hot and expanding rapidly. There's only so much you can do with physics. Another proposed explanation involves black holes. We know that supermassive black holes sit at the centers of most large galaxies, including our own Milky Way. These black holes can be millions or even billions of times the mass of the Sun. In the current epoch, we understand roughly how they form. They start as smaller black holes left behind when massive stars die, and then they grow by swallowing gas and merging with other black holes over billions of years. But Webb has found evidence that supermassive black holes already existed in the very early universe. This presents the same problem as the galaxies themselves. How do you get something that big, that fast? There has not been enough time for it to grow through the normal processes. Some scientists have proposed that there might be a way for black holes to form directly from the collapse of enormous gas clouds in the early universe. These would be called direct collapse black holes. They would skip the intermediate step of first becoming a star and then collapsing. Instead, the whole cloud would fall in on itself and form a black hole right away. This could create seed black holes that are much larger than what you get from dying stars, giving them a head start on growing into the monsters we see at the centers of galaxies. Whether this actually happened is still being debated. The conditions required for direct collapse are very specific. The gas cloud needs to avoid fragmenting into smaller pieces. It needs to avoid forming stars before it can collapse as a whole. There are questions about how common such conditions might have been in the early universe. Another possibility that some scientists have raised is even more radical. What if the universe is older than we think? The age of the universe is calculated based on the expansion rate and the distance to the most distant objects we can see. If there is something about those calculations that is off, it could change the timeline. This idea challenges some very fundamental assumptions. The age of the universe is one of the most basic numbers in cosmology. It is tied to our understanding of the cosmic microwave background, the distribution of galaxies, and the behavior of the expansion itself. Changing it would have ripple effects throughout all of physics. Most scientists are not ready to go that far, but the fact that the possibility is even being discussed shows just how strange the Webb observations really are. As I mentioned earlier, there is a concept in cosmology called the lambda CDM model. This model includes two mysterious components that we do not fully understand. Lambda refers to dark energy, the force that seems to be driving the accelerating expansion of the universe. Cold, dark matter refers to the invisible particles that provide most of the gravitational mass holding galaxies together. Dark energy is particularly strange. It makes up about 68% of the total energy content of the universe. Yet we have no idea what it actually is. We just know that something is pushing the universe apart faster and faster over time. Dark matter is another 27%. That leaves only about 5% for ordinary matter, the stuff that makes up stars, planets, and people. Our models of the early universe assume that dark energy and dark matter behaved in certain ways. If those assumptions are wrong, it could change the timeline significantly. Some physicists have proposed modifications to dark energy called early dark energy. In these models, dark energy was stronger in the early universe than it is today. This would have affected the expansion rate and potentially changed how fast structures could form. Testing these ideas requires incredibly precise observations. The good news is that we are getting better at making such observations all the time. Webb is just one of many new instruments that are pushing the boundaries of what we can see and measure. Ground-based telescopes are improving too, along with radio telescopes and gravitational wave detectors. Let us step back for a moment and consider what all of this means. We have spent decades building up a detailed picture of cosmic history. We have traced the evolution of the universe from its first moments to the present day. We have mapped the distribution of galaxies across billions of light years. We have measured the age of the universe to within a fraction of a percent. And now, one telescope has found something that does not fit, something that challenges the whole picture. This is not a crisis for science. This is science working exactly as it should. Science advances by making predictions and then testing them against observations. When the observations do not match the predictions, it means we have something new to learn. The impossible galaxies found by Webb are a gift. They are telling us that there is something about the universe we do not yet understand. Maybe it is something small, a tweak to our models of early star formation. Maybe it is something big, a fundamental revision to our understanding of cosmology itself. Either way, it is an opportunity to learn. History is full of moments like this, moments when new observations challenged existing theories and forced scientists to think in new ways. When Galileo pointed his telescope at Jupiter and saw moons orbiting it, he challenged the idea that everything in the sky revolved around Earth. When astronomers discovered that the universe was expanding, they challenged the assumption that the cosmos was static and eternal. When scientists found that the expansion was accelerating, they had to invent a whole new concept, dark energy, to explain it. Each of these discoveries felt shocking at the time. Each one forced people to revise their understanding of reality. And each one ultimately led to a deeper, richer, more accurate picture of the universe. The same thing is happening now. Webb's impossible galaxies are the latest challenge. They are forcing us to question assumptions we did not even know we were making. They are opening up new lines of research, new theoretical possibilities, new ways of thinking about the cosmos. What makes this moment special is the speed at which it is happening. Webb has been operational for only a few years, and already it has transformed our understanding of the early universe. Every new observation brings more data. Every new paper raises new questions. The pace of discovery is exhilarating, and we're just getting started. Webb has a planned mission lifetime of at least 10 years, possibly longer. The data it has collected so far is only a small fraction of what it will eventually gather. As it continues to observe the universe, it will find more surprises, more impossible objects, more puzzles for scientists to solve. Beyond Webb, there are other missions in the works. The Nancy Grace Roman Space Telescope is scheduled to launch in a few years. It will have a field of view 100 times larger than Hubble, allowing it to survey huge swaths of the sky at once. The European Space Agency is working on additional missions as well. On the ground, new observatories are coming online that will complement what we learn from space. The Vera C. Rubin Observatory in Chile will create a complete map of the southern sky every few nights, allowing scientists to track changes over time. The extremely large telescope, also in Chile, will have a primary mirror nearly 40 meters across, dwarfing anything that exists today. Together, these instruments will give us an unprecedented view of the universe. They will allow us to test our theories with exquisite precision. They will reveal new phenomena that we cannot even imagine today. So what have we learned from this story? So far, we have learned that the James Webb Space Telescope found galaxies in the early universe that should not exist according to our models. We have learned that these galaxies are too massive, too mature, and too well organized for the time period in which they appear. We have learned that scientists are scrambling to explain the observations, proposing everything from new modes of star formation to modifications of fundamental cosmological parameters. But there is more to this story, because as remarkable as the impossible galaxies are, they are not the only thing Webb has found that challenges our understanding. The telescope has also been looking at the era right after the Big Bang, the period known as cosmic dawn. And what it has found there is just as surprising. Cosmic dawn is the name we give to the period when the first stars and galaxies began to shine. Before this era, the universe was filled with a fog of neutral hydrogen. This fog blocked light, making the universe essentially opaque. Then, as the first stars formed and began to emit ultraviolet radiation, that radiation began to ionize the surrounding hydrogen, stripping away electrons and making the gas transparent. This process is called reionization. It was a gradual process, spreading outward from the first sources of light like dawn spreading across a landscape. By the time the universe was about 1 billion years old, the process was complete. Space became transparent, allowing light to travel freely across cosmic distances. Our models predicted that reionization was a slow, gradual process. The first stars were supposed to form in small, isolated pockets. Their light would ionize the hydrogen immediately around them, creating bubbles of clear space in the otherwise foggy universe. Over time, these bubbles would grow and merge until the whole universe was ionized. But Webb's observations suggest that ionization may have happened differently than we thought. The impossible galaxies that Webb found would have produced enormous amounts of ultraviolet light. If such galaxies were common in the early universe, they would have ionized the hydrogen much faster than our models predicted. The bubbles would have grown more quickly, the dawn would have arrived sooner. This connects to another observation that has puzzled scientists for years. Measurements of the cosmic microwave background, the afterglow of the Big Bang, contain information about when ionization happened. Some of these measurements have hinted that ionization might have started earlier or proceeded faster than expected. The Webb observations of massive, early galaxies could help explain why. Everything is connected. The impossible galaxies are not just an isolated anomaly. They tie into the broader picture of how the universe evolved from its earliest moments to the present day. Understanding them will require rethinking not just the formation of galaxies, but the entire timeline of cosmic history. Now let us turn to an even more mysterious aspect of what Webb has found. I mentioned earlier that Webb discovered evidence of supermassive black holes in the very early universe. This is perhaps the most puzzling observation of all. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive stars run out of fuel and collapse under their own weight. The core of the star compresses into an incredibly dense point called a singularity, surrounded by an event horizon beyond which there is no return. Stellar black holes, the kind formed from individual stars, typically have masses ranging from a few times to a few tens of times the mass of our Sun. But at the centers of galaxies, we find something much larger. Supermassive black holes can have masses of millions to billions of solar masses. Our own Milky Way has a supermassive black hole at its center called Sagittarius A star. It has a mass of about 4 million suns. The black hole at the center of the M87 galaxy is even more massive, at over 6 billion solar masses. We actually have an image of that one thanks to the Event Horizon Telescope. How do supermassive black holes form? That is one of the great unsolved puzzles in astrophysics. In the current universe, we can understand how they might grow over time. They swallow gas and dust that falls toward them. They merge with other black holes when galaxies collide. Over billions of years, they can grow from modest sizes to enormous ones. But Webb has found evidence of supermassive black holes that existed when the universe was less than 1 billion years old. These black holes had masses of millions or even hundreds of millions of solar masses. That is way too big for the amount of time available. The problem is growth rate. There is a limit to how fast a black hole can swallow material. When gas falls toward a black hole, it heats up and radiates energy. This radiation pushes back against the infalling material, slowing down the feeding process. This limit is called the Eddington limit, named after the astrophysicist Arthur Eddington. If you start with a stellar mass black hole, something around 10 or 20 solar masses, and let it feed at the maximum possible rate for 700 million years, it simply cannot grow big enough to match what Webb observed. The math does not work out. You need either a bigger starting point or a faster growth rate. This is where the idea of direct collapse black holes comes in again. If massive black holes could form directly from collapsing gas clouds in the early universe, without first becoming stars, they could start out much heavier. A seed black hole of 10,000 or 100,000 solar masses would have a much easier time growing to supermassive scales in the available time. Another possibility is that black holes in the early universe somehow exceeded the Eddington limit. Maybe the conditions back then allowed for super Eddington accretion, where material falls in faster than the normal limit would allow. This could happen if the infalling material is particularly dense, or if the geometry of the accretion is different than what we normally see. Some researchers have even speculated about primordial black holes. These would be black holes that form not from collapsing stars, but from density fluctuations in the very early universe, moments after the Big Bang itself. If the density in some regions was high enough, those regions might have collapsed directly into black holes while the universe was still a fraction of a second old. Primordial black holes are a theoretical concept that has been around for decades. They have been proposed as a possible explanation for dark matter. If space is filled with huge numbers of small primordial black holes, they could provide the gravitational mass that we attribute to dark matter. Most evidence has disfavored this idea, but the possibility has never been completely ruled out. If primordial black holes exist, and if some of them had masses of thousands or tens of thousands of solar masses, they could serve as the seeds for the supermassive black holes we see in early galaxies. This would solve the timing problem because the seeds would have been around since the very beginning of the universe. Testing these ideas is incredibly difficult. Primordial black holes, if they exist, would be essentially invisible unless they are actively swallowing material. And even then, distinguishing them from regular black holes would be a challenge. But the Webb observations are driving renewed interest in these exotic possibilities. Let me take a moment to appreciate how far we have come. A century ago, we did not even know that other galaxies existed. 50 years ago, we could not observe the early universe at all. 20 years ago, the best instruments we had could only catch fuzzy glimpses of cosmic dawn. Now, with Webb, we are seeing individual galaxies from when the universe was less than 5% of its current age. We are watching black holes grow in the first billion years of cosmic history. We are testing our theories in ways that were science fiction a generation ago. And we are finding that our theories need work. That is not a failure, that is progress. Every time we find something that does not fit, we learn something new. Every anomaly is a clue pointing us toward a deeper understanding. The impossible galaxies and the early supermassive black holes are two pieces of a larger puzzle. But there are other pieces too, other observations from Webb that add to the mystery. One of these involves the chemical composition of early galaxies. Stars produce heavy elements through nuclear fusion in their cores and through explosive supernova deaths. These heavy elements, things like carbon, oxygen, nitrogen, and iron, are essential for the formation of rocky planets and eventually life. In the early universe, before many generations of stars had lived and died, heavy elements should have been rare. Our models predicted that the first galaxies would be chemically primitive, composed almost entirely of hydrogen and helium with only trace amounts of heavier elements. But Webb has found galaxies in the early universe that have surprisingly high abundances of certain elements. Some galaxies show more nitrogen than expected, or more carbon, or unusual ratios between different elements. These chemical signatures tell us about the types of stars that existed in those early galaxies. The presence of certain elements suggests that particular kinds of stellar processes were happening. If the chemical abundances do not match our predictions, it means our picture of early star formation is incomplete. One possibility is that the first stars really were unusual. The massive primordial stars I mentioned earlier, the ones that formed from pure hydrogen and helium, would have produced heavy elements in different proportions than normal stars. When they exploded, they would have seeded space with a particular mix of chemicals that might not match what later generations of stars produced. Another possibility is that there were exotic processes happening in those early galaxies that we have not accounted for. Maybe there were unusual types of supernovae, or maybe the interstellar medium was dense enough that heavy elements were retained rather than blown away. The chemistry of the early universe is still poorly understood. Webb is also revealing surprises about the structure of early galaxies. I mentioned that some of the impossible galaxies have spiral arms, like our own Milky Way. This is surprising because spiral structure is thought to develop slowly over time through gravitational interactions and density waves in the galactic disk. But the surprises go beyond just spiral arms. Webb has found galaxies in the early universe that have distinct bars across their centers. These bars are linear structures of stars that stretch across the middle of a galaxy, connecting the spiral arms. Barred spiral galaxies are common in the local universe. The Milky Way has a bar, but they were not expected to exist so early in cosmic history. The formation of a galactic bar requires the galaxy to have a well-established disk of stars moving in orderly orbits. It requires certain gravitational conditions to be met. It takes time. And yet there they are, bars in galaxies from when the universe was barely out of infancy. Each new observation adds another layer to the puzzle. Each discovery raises new questions. The early universe was not the simple, chaotic place we expected. It was already complex, already structured, already mature in ways we did not anticipate. So where does this leave us? What do scientists actually do when faced with observations that contradict their models? The first thing they do is gather more data. Webb is still observing. Every day, it collects more photons from the distant universe. Every new image potentially contains more impossible galaxies, more early black holes, more chemical anomalies. The more data we have, the better we can understand what is really going on. The second thing scientists do is refine their analyses. When you are pushing the limits of what is observable, there is always a chance that some subtle effect is distorting your measurements. Calibration errors, instrument quirks, atmospheric effects for ground-based telescopes, all of these can introduce biases. By carefully checking and rechecking the data, scientists can separate real signals from artifacts. The third thing scientists do is develop new theories. When the old models cannot explain the observations, you need new models. This is where creativity comes in. Theorists take the observations as constraints and ask what physical processes could produce them. They propose new mechanisms, new parameters, new frameworks. Then they make predictions that can be tested against future observations. This back and forth between theory and observation is the heartbeat of science. It is how we have learned everything we know about the universe. And it is happening right now in real time as scientists around the world grapple with what Webb has revealed. Let me tell you about some of the theoretical responses to the impossible galaxies. One approach is to modify the physics of early star formation. In the standard model, stars form when clouds of gas collapse under their own gravity. The process is regulated by cooling. Gas needs to lose energy to continue collapsing, and by magnetic fields, pressure, and turbulence. In the early universe, the conditions were different. The gas was hotter and more diffuse. There were no heavy elements to help with cooling. The magnetic fields were weaker. These differences might have led to a different mode of star formation, one that was more efficient than what we see today. Some researchers have proposed that star formation in the early universe was top-heavy, meaning that a larger fraction of stars formed with high masses. High-mass stars are brighter and produce more energy. If the early universe was dominated by such stars, it would explain why the first galaxies were so luminous. Other researchers have focused on the role of feedback. When stars form, they emit radiation and stellar winds that can heat up the surrounding gas and blow it away. This feedback can slow down or even stop future star formation. But if feedback was less effective in the early universe, perhaps because of different gas densities or compositions, then star formation could have proceeded more rapidly. There are also proposals that involve dark matter. In the standard model, dark matter forms halos that provide the gravitational scaffolding for galaxy formation. Ordinary matter falls into these halos and coalesces into galaxies. The properties of dark matter halos determine how quickly galaxies can form and how massive they can become. If dark matter behaves differently than we thought, it could change the timeline. Some alternative dark matter models allow for more concentrated halos in the early universe, which would accelerate galaxy formation. Other models involve interactions between dark matter and ordinary matter that could enhance structure formation. Then there are the proposals that involve modifying the expansion history of the universe. The expansion rate is not constant. It was faster in the early universe and has been accelerating in recent times due to dark energy. The exact history of this expansion affects everything from the age of the universe to the rate at which structures form. If the expansion history was different than the standard model predicts, it could reconcile the Webb observations with theory. Models of early dark energy, which I mentioned earlier, are one example. These models propose that dark energy had a larger effect in the early universe than it does today, which would change the relationship between cosmic time and the formation of structures. Testing these theoretical proposals requires more than just Webb observations. It requires combining data from multiple sources and looking for consistency. If a model explains the impossible galaxies but fails to match the cosmic microwave background, then it is probably wrong. The true explanation will have to account for all the evidence, not just the new anomalies. This is what makes cosmology so challenging and so exciting. We are trying to understand the entire universe from our little vantage point on Earth. We are trying to reconstruct billions of years of history from the light that reaches our telescopes. We are trying to figure out the rules of physics that govern everything that exists, and we are making progress. Despite the challenges posed by the Webb observations, we are learning more about the universe than ever before. The impossible galaxies are not the end of the story. They are the beginning of a new chapter. Let us now dive deeper into one of the most fascinating aspects of the Webb discoveries. The telescope has not only shown us that massive galaxies existed in the early universe, it has also given us clues about what was happening inside those galaxies. And what it has found is remarkable. Webb's instruments can break down the light from distant galaxies into its component wavelengths. This process, called spectroscopy, reveals the chemical fingerprints of the stars and gas in those galaxies. Different elements absorb and emit light at specific wavelengths. By analyzing the spectrum of a galaxy, astronomers can determine what elements are present and in what quantities. The spectra of early galaxies have been full of surprises. As I mentioned, some galaxies show unexpectedly high levels of certain elements, but there is more to the story than just abundances. The spectra also reveal the physical conditions inside these galaxies, things like temperature, density, and the state of ionization. One of the most striking findings is that many early galaxies show evidence of intense star formation. The spectra contain emission lines, bright features at specific wavelengths, that indicate the presence of hot gas being heated by young stars. These emission lines are stronger than expected, suggesting that star formation was happening at a furious pace. In some cases, the spectra suggest that these galaxies were forming stars at rates hundreds of times higher than the Milky Way today. This is consistent with the idea that the early universe was more active than we thought, but it also raises questions. Where did all that gas come from? How could star formation proceed so rapidly without burning through all the available fuel? The spectra have also revealed the presence of active galactic nuclei in some early galaxies. An active galactic nucleus is a region at the center of a galaxy where a supermassive black hole is actively swallowing material. As matter falls toward the black hole, it heats up to extreme temperatures and emits enormous amounts of radiation. This radiation can outshine the entire rest of the galaxy. Finding active galactic nuclei in very early galaxies confirms that supermassive black holes were already in place and already feeding. This connects to the mystery I discussed earlier about how such black holes could have grown so large in such a short time. The spectroscopic evidence shows that these black holes were not just present but actively growing, swallowing material at prodigious rates. Some of the early active galactic nuclei discovered by Webb are among the most distant and therefore oldest objects ever detected. They existed when the universe was less than 500 million years old. Seeing them in such detail is like having a window into the very beginnings of galaxy evolution. The spectra have revealed another surprise as well. Some early galaxies show signs of powerful outflows, gas being ejected from the galaxy at high speeds. These outflows are likely driven by the combined energy of supernovae and active galactic nuclei. They are important because they regulate star formation. By ejecting gas from the galaxy, they can slow down or stop the creation of new stars. The presence of outflows in early galaxies suggests that feedback processes were already at work. This is interesting because feedback is thought to be one of the main factors that limits the growth of galaxies. If feedback was already operating in the very early universe, it means the conditions for galaxy formation were more similar to today than we might have expected. All of this spectroscopic information is helping scientists build a more detailed picture of the early universe. It is not enough to know that massive galaxies existed. We need to understand how they worked, what was happening inside them, and how they evolved over time. Webb's spectra are giving us that information in unprecedented detail. Let me now shift focus to another aspect of the Webb discoveries that has captured the imagination of scientists and the public alike. I'm talking about the search for the very first light in the universe, the light from the first stars that ever shone. The first stars, sometimes called population 3 stars, have never been directly observed. They are a theoretical prediction based on our understanding of how stars form from primordial gas. These stars would have been different from any stars that exist today. They would have been massive, perhaps hundreds of times the mass of the sun. They would have been hot and blue, burning through their fuel in just a few million years. and they would have lived and died so long ago that their light has been traveling toward us for almost the entire age of the universe. Detecting the light from population 3 stars is one of the ultimate goals of observational cosmology. It would confirm our theories about the formation of the first stars, it would tell us about the conditions in the early universe, and it would be a stunning achievement, seeing light from the very first objects to ever shine in a previously dark cosmos. Webb was designed with this goal in mind. Its sensitivity to infrared light makes it the best tool we have for searching for population 3 stars. The light from these stars, originally emitted in the ultraviolet, has been redshifted by the expansion of the universe into the infrared bands that Webb can see. So far, Webb has not definitively detected light from individual population 3 stars, but it has found tantalizing hints. Some of the early galaxies show spectroscopic signatures that could be consistent with the presence of primordial stars. There are certain emission lines, particularly from ionized helium, that would be enhanced if a galaxy contained a population of extremely hot, massive stars. These hints are still being investigated. It is possible that the signatures are due to other processes like active galactic nuclei or unusual types of ordinary stars. More observations and more careful analysis are needed to determine whether we are actually seeing evidence of the first stars. Even if Webb never detects population 3 stars directly, it is already teaching us about them indirectly. By observing the galaxies that came just after the era of the first stars, we can learn about the conditions they left behind. The chemical abundances, the level of ionization, the structure of early galaxies, all of these contain information about what came before. There is also hope that future telescopes will succeed where Webb has not yet. The next generation of ground-based observatories, like the Extremely Large Telescope, will have even better sensitivity and resolution. They might be able to pick out individual bright stars in the most distant galaxies, potentially including population 3 survivors or the remnants of their explosive deaths. The search for the first light is a quest that spans decades of effort and multiple generations of astronomers. Webb has brought us closer than ever before. Even if the final answer remains elusive for now, the journey itself is revealing wonders we never imagined. Now let us consider the philosophical implications of what Webb has discovered. Science is not just about gathering facts. It is about building a coherent picture of reality. And when that picture is challenged, it forces us to think deeply about what we know and how we know it. For decades, the lambda-CDM model has been our best description of the universe. It is based on general relativity, the theory of gravity developed by Albert Einstein. It includes mysterious components like dark matter and dark energy, and it makes specific, testable predictions about the history and structure of the cosmos. The success of lambda-CDM has been remarkable. It correctly predicted the patterns we see in the cosmic microwave background. It explained the observed distribution of galaxies. It matched the measurements of cosmic expansion. Whenever we have tested it, it has passed. But no theory is perfect. Every theory is a model, an approximation of reality that captures some aspects while ignoring others. The question is always how well the model matches the observations and whether any discrepancies are significant. The Webb observations are a significant discrepancy. They show that our model of the early universe is incomplete at best and possibly fundamentally flawed. This does not mean lambda-CDM is wrong in some absolute sense. It means there are aspects of cosmic history that it does not adequately describe. Science progresses by finding these discrepancies and resolving them. Sometimes the resolution is a small adjustment, a tweak to a parameter, or the addition of a minor effect. Sometimes it requires a more radical revision, a new theory that replaces the old one. We do not yet know which category the Webb observations fall into. What we do know is that the universe is more complex and more surprising than we expected. The early cosmos was not a simple, quiet place waiting for structure to slowly emerge. It was a dynamic, active environment where massive galaxies and supermassive black holes formed with astonishing speed. Whatever processes drove this rapid formation, they represent physics that our models do not yet capture. This is humbling. It reminds us that our understanding of the universe is still a work in progress. We have learned an enormous amount over the past century, but there is so much more to discover. The universe has been around for nearly 14 billion years. We have been doing science for only a few hundred. It would be surprising if we had already figured everything out. But it is also inspiring. Every gap in our understanding is an opportunity for discovery. Every anomaly is a doorway to new knowledge. The impossible galaxies that Webb found are not problems to be lamented. They are gifts to be celebrated. They are telling us that there is something exciting waiting to be learned. Let me now turn to some specific discoveries that have emerged from Webb in the months and years since its launch. Each of these adds another piece to the puzzle, another detail to the emerging picture of the early universe. One remarkable observation involves a galaxy known by the catalog designation Ceres 1019. This galaxy existed when the universe was about 600 million years old. What makes it special is its shape. Even at that early time, this galaxy shows a clear bar structure across its center, something that was thought to take billions of years to develop. Bars form in disk galaxies through a particular type of gravitational instability. When stars orbit in a disk, their collective gravity can create patterns that rotate through the galaxy. Under certain conditions, these patterns can grow into a linear bar that stretches across the center. This process requires a mature, settled disk with stars moving in orderly orbits. It was not supposed to happen so early in cosmic history. The discovery of Ceres 1019 and other barred galaxies in the early universe challenges our understanding of how galactic structure develops. Either bars can form much faster than we thought, or the conditions in early galaxies were different than our models predict. Either way, it is another piece of evidence that the early universe was more evolved than expected. Another striking discovery involves galaxy mergers. When two galaxies collide, their stars pass by each other without direct contact, but their gas clouds smash together and trigger bursts of star formation. The gravitational interactions warp and distort both galaxies, creating tidal tails and bridges of stars that stretch across space. Galaxy mergers are common in the universe. They are one of the main ways that galaxies grow larger over time. Our own Milky Way is destined to merge with the Andromeda Galaxy in a few billion years. The process takes hundreds of millions of years to complete and leaves distinctive signatures that can be observed. Webb has found evidence of galaxy mergers in the very early universe. Some of the distant objects it observed appear to be pairs or groups of galaxies in the process of combining. This is not entirely surprising since mergers are a fundamental part of galaxy formation. But the details of what Webb sees are challenging our models. In some cases, the merging galaxies appear to be much more massive than expected for that era. The amount of material involved suggests that substantial galaxy building had already occurred before the mergers began. This reinforces the picture that the early universe was more active and more advanced than the standard model predicts. In other cases, the geometry of the mergers is unusual. Some early galaxy systems seem to have 3 or 4 members interacting at once, rather than the simple binary mergers that are most common today. This could indicate that the environment was different in the early universe, with galaxies packed more closely together and interactions more frequent. Webb has also discovered examples of extremely compact galaxies in the early universe. These are galaxies that pack a lot of mass into a very small volume. They are much denser than typical galaxies today. In fact, some of them are so compact that their central regions rival the density of globular clusters, the tight balls of ancient stars that orbit around galaxies. These compact galaxies raise interesting questions. How did so much mass get compressed into such a small space? What prevented the gas from spreading out during the formation process? And what happened to these galaxies over the billions of years since they formed? Did they stay compact, or did they eventually puff up and spread out? Observations of galaxies in the more recent universe have found examples of compact objects called red nuggets. These are thought to be the descendants of the compact early galaxies that Webb is now seeing. Over time, they may have grown larger through minor mergers, accreting smaller galaxies around them like a snowball rolling down a hill. But the core remains dense, a fossil record of the conditions under which the galaxy originally formed. By studying both the early compact galaxies with Webb and their modern descendants with other telescopes, astronomers can trace the evolution of these systems across cosmic time. This is giving us insights into how galaxies change and grow over billions of years. Another area where Webb has made surprising discoveries is in the connection between galaxies and their surrounding environments. Galaxies do not exist in isolation. They are embedded in vast networks of gas and dark matter called the cosmic web. This web consists of filaments, sheets, and knots of matter that stretch across the universe, with galaxies forming at the densest points. The structure of the cosmic web is determined by the initial conditions of the universe and the properties of dark matter. Our models make specific predictions about what this web should look like at different cosmic epochs. Webb has the ability to test these predictions by observing how galaxies were distributed in the early universe. Some Webb observations have found evidence of protoclusters, regions where multiple galaxies are beginning to clump together under their mutual gravity. These protoclusters are the seeds of the massive galaxy clusters we see today, containing hundreds or thousands of galaxies bound together. Finding protoclusters in the early universe is not surprising in itself. We expected them to be there. What is surprising is how developed some of them appear to be. The galaxies within these early protoclusters are interacting, forming stars, and already showing signs of the environmental effects that shape cluster galaxies today. The level of activity suggests that structure formation was proceeding more rapidly than predicted. There are also hints that the cosmic web itself might have been more pronounced in the early universe. Some observations suggest that filaments of gas-connecting galaxies were denser and more luminous than expected. If confirmed, this could indicate that matter was more concentrated along these cosmic highways, funneling material into galaxies faster than our models allow. These observations of the large-scale environment complement the studies of individual galaxies. Together, they paint a picture of an early universe that was already well on its way to building the structures we see today. The foundations were being laid faster than we thought, with more material and more energy than our models accounted for. Let me now discuss a topic that might seem slightly tangential but is actually central to understanding what Webb has found. I am talking about the nature of time in cosmology and how we interpret what we see when we look into the distant universe. When astronomers say that a galaxy is 13 billion light-years away, they mean that the light from that galaxy has been traveling for 13 billion years to reach us. But what exactly does that mean? The universe has been expanding during all that time. The space between us and that galaxy has been stretching. The distance is not static but dynamic. There are actually several different ways to define distance in cosmology, and they give different numbers. The light travel distance is the time it took for the light to reach us, measured in light years. The co-moving distance is the current proper distance to the galaxy, accounting for the expansion that happened while the light was traveling. The angular diameter distance relates the apparent size of the galaxy to its true physical size. These different distance measures all increase as we look at more distant objects, but they increase at different rates. For very distant objects, the co-moving distance can be much larger than the light travel distance because of all the expansion that has occurred. This matters for understanding the impossible galaxies. When we say these galaxies existed when the universe was only a few 100 million years old, we are talking about the age of the universe at the time the light was emitted. The galaxies themselves no longer exist in the form we see. They have evolved over the billions of years since, merging with other galaxies, forming new stars, changing in countless ways. What we see is a snapshot from the distant past. The light that reaches Webb is a fossil, a record of what was happening in that long-ago era. By collecting enough of these fossils from different distances, we can reconstruct the history of the universe, seeing how things changed over time. This is the essence of observational cosmology. We cannot watch the universe evolve in real time. The timescales are far too long for that. Instead, we look at different distances, knowing that different distances correspond to different times. The more distant objects show us older times. The closer objects show us more recent times. By comparing them, we build up a picture of cosmic evolution. The Webb observations are giving us our clearest view yet of the earliest times. The impossible galaxies, the early black holes, the chemical abundances, the galactic structures, all of this is information about what the universe was like in its youth, and the picture that is emerging is more complex and more surprising than anyone anticipated. This brings me to an important point about the nature of scientific discovery. Sometimes people think that science advances by confirming what we already believe. A theory makes a prediction, the prediction is tested, the prediction is confirmed, and the theory is considered proven. This does happen, but it is only part of the story. The more interesting moments in science come when predictions fail. When the observations do not match what we expected, that is when we learn something truly new. The failure of a prediction tells us that our understanding is incomplete. It points us toward the unknown and challenges us to expand our knowledge. The Webb observations are a perfect example. The Lambda CDM model made predictions about what we should see in the early universe. Webb tested those predictions and found that some of them were wrong. This is not a failure of Webb or a failure of the scientists who built the model. It is a success of the scientific process. We have learned that there is more to discover. The history of cosmology is full of such moments. When astronomers first measured the expansion rate of the universe, they got a number that seemed too high. It implied an age of the universe that was younger than the oldest stars, an obvious contradiction. This anomaly led to decades of refinement in both observations and theory until the contradiction was resolved. When astronomers discovered the cosmic microwave background, it was a surprise. They were not looking for it. They stumbled upon it while trying to eliminate noise from a radio antenna. Yet this accidental discovery provided the strongest evidence for the Big Bang and transformed our understanding of cosmic origins. When astronomers found that the expansion of the universe is accelerating, it was shocking. For decades, everyone had assumed that the expansion was slowing down due to gravity. The discovery of acceleration forced the invention of dark energy, a mysterious force that permeates all of space. Each of these discoveries challenged existing assumptions and led to breakthroughs in understanding. The Webb observations are the latest in this tradition. They are showing us that our picture of the early universe needs revision. The exact nature of that revision is still being worked out, but there is no doubt that something important is waiting to be learned. Let us now explore some of the more speculative ideas that have been proposed to explain the Webb observations. I want to be clear that these are not mainstream theories. They are possibilities that scientists are exploring, some more seriously than others, but they give a sense of the range of thinking that is happening in response to these surprising discoveries. One idea that has been floated is that the fundamental constants of nature might have been different in the early universe. The laws of physics include certain numbers like the strength of gravity or the mass of an electron that appear to be constant throughout space and time. But what if they are not? What if some of these constants were different in the distant past? If the strength of gravity were slightly different in the early universe, it could change the rate at which structures formed. Stronger gravity would pull matter together faster, potentially explaining the rapid appearance of massive galaxies. Similarly, changes in other constants could affect nuclear reactions in stars, altering how quickly heavy elements were produced. This idea is highly speculative. There is no strong evidence that fundamental constants have changed over time. In fact, there are tight constraints from various observations that limit how much variation is possible. But the idea has not been completely ruled out, and the Webb observations have renewed interest in testing it more carefully. Another speculative idea involves modifications to general relativity itself. Einstein's theory of gravity has passed every test we have thrown at it for over a century. It explains the motion of planets, the bending of light around massive objects, the existence of black holes, and the expansion of the universe. It is one of the most successful theories in the history of physics. Yet there are reasons to think that general relativity might not be the final word on gravity. It does not mesh well with quantum mechanics, the theory that governs the behavior of matter at the smallest scales. This incompatibility suggests that there might be a deeper theory of gravity that reduces to general relativity in most situations but differs in extreme conditions. The early universe was certainly an extreme condition. Densities were enormous. Temperatures were unimaginably high. If gravity behaved differently under these conditions, it could affect the formation of structures in ways that our current models do not capture. Some physicists have explored modified theories of gravity that could enhance structure formation in the early universe while still matching all the tests that general relativity passes in the present. Yet another idea involves the possibility of multiple populations of dark matter. In the standard model, dark matter is a single type of particle that interacts only through gravity. But there is no reason it has to be so simple. Dark matter could consist of multiple species with different properties. Some might be heavier, some lighter. Some might interact with ordinary matter, some might not. If dark matter had a more complex nature, it could affect structure formation in subtle ways. Different species might cluster on different scales, enhancing the formation of galaxies in some regions while suppressing it in others. The Webb observations could be pointing us toward a richer picture of dark matter than we currently have. Then there are even more exotic possibilities. Some physicists have speculated about extra dimensions of space, hidden from our direct observation but affecting the behavior of gravity. Others have considered the role of cosmic strings, hypothetical defects in the fabric of space-time left over from the early universe. Still others have explored the implications of various quantum gravity theories that might change how we think about cosmic evolution. None of these ideas is currently favored by the majority of scientists. The simplest explanation is usually that our models of ordinary physics in the early universe need adjustment, not that we need to invoke exotic new physics. But the fact that so many possibilities are being considered shows just how profound the Webb observations are. They are shaking up the field in a way that does not happen very often. I should also mention that not everyone agrees on how serious the Webb anomalies really are. Science is full of disagreements, and that is healthy. Some researchers argue that the impossible galaxies are not quite as impossible as they first appeared. They point out uncertainties in the measurements, possible sources of error, and alternative interpretations of the data. For example, the masses of distant galaxies are estimated from their brightness. A galaxy that appears brighter is assumed to contain more stars and therefore more mass. But what if the stars in early galaxies were brighter than average? What if they were dominated by massive, luminous stars rather than the mix we see today? In that case, the galaxies might not be as massive as they appear. This is a valid concern, and researchers are working hard to address it. By studying the spectra of early galaxies in detail, they can learn about the types of stars they contain. By observing multiple properties beyond just brightness, they can build a more complete picture of what is really going on. Another source of uncertainty involves the redshifts used to determine distances. Redshift measures how much the light has been stretched by cosmic expansion. The higher the redshift, the more distant and older the galaxy. But in some cases, other effects can mimic high redshifts. Certain types of emission from galaxies can shift the apparent color of the light, potentially fooling the analysis. Astronomers are careful about this. They use multiple methods to confirm redshifts, including spectroscopic observations that identify specific spectral lines from known elements. The galaxies that have caused the most controversy have been confirmed by spectroscopy, making it unlikely that their redshifts are wrong. Still, the debate continues. This is how science works. Different researchers interpret the same data in different ways. They argue, they test, they gather more evidence. Over time, the truth emerges. The process can be messy, but it works. What is clear at this point is that Webb has revealed something unexpected. Whether it requires a complete overhaul of cosmology or just some tweaks to existing models, we have learned that the early universe was not what we thought. That alone is a major achievement. Now let us consider what all of this means for humanity's place in the cosmos. This is where the science becomes personal, where the abstract discoveries about distant galaxies connect to our own existence here on Earth. We are made of matter that was forged in the hearts of stars. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of this came from stars that lived and died billions of years ago. When those stars exploded, they scattered their enriched material into space, where it eventually coalesced into new stars, planets, and ultimately life. This means we are connected to the cosmic story in a very direct way. The history of the universe is our history. The evolution of galaxies and stars is the prelude to our own existence. Every discovery about the early cosmos is a discovery about our origins. The impossible galaxies that Webb found are part of this story. They represent a chapter in cosmic history that we did not know about. Whatever processes formed those galaxies, whatever physics was at work, it contributed to the chain of events that eventually led to us. If massive galaxies formed earlier than we thought, it means the universe was producing stars and heavy elements earlier than we thought. It means the raw materials for planets and life were available sooner. It does not necessarily mean that life arose earlier, because there are many other factors involved, but it changes the timeline, the context in which life eventually emerged. Consider the implications for the search for life elsewhere in the universe. We know that life on Earth took billions of years to evolve from simple microbes to the complex organisms we see today. We also know that Earth itself took time to form and cool down enough for life to arise. If you add up all the time needed, you might conclude that intelligent life could not appear until fairly late in cosmic history. But the Webb observations suggest that the universe was cooking up stars and heavy elements faster than we assumed. This could mean that the conditions for life appeared earlier in more places. It does not prove that life exists elsewhere, but it expands the possibilities. It suggests that the universe might have been hospitable to life for longer than we thought. Of course, we still do not know how common life is. We have only one example, Earth, and we do not fully understand how life arose here. The origin of life remains one of the great unsolved mysteries. But every piece of evidence about the history of the cosmos helps us frame the question better. The Webb observations are giving us new information to work with. There's also a deeper philosophical point here. The universe is not static. It is not a fixed backdrop against which events unfold. The universe itself is evolving, changing, developing. Galaxies form and merge, stars are born and die. Structures grow more complex over time. This cosmic evolution is the context for our existence. We are part of a vast, ongoing process that has been unfolding for nearly 14 billion years. The atoms in our bodies have been through countless transformations, from primordial hydrogen to stellar fusion products, to planetary material to living tissue. We are not separate from the universe, we are expressions of it. Understanding cosmic evolution is therefore a way of understanding ourselves. When we learn about the early universe, we learn about where we came from. When we discover surprises like the impossible galaxies, we learn that our origins are more complex and more interesting than we realized. This perspective can be humbling and inspiring at the same time. It is humbling because it reminds us how small we are compared to the vastness of space and time. Our entire civilization, all of human history, is just a tiny sliver of the cosmic story. We are newcomers to a universe that was already ancient when our species emerged. But it is also inspiring because it shows how far we have come. A few thousand years ago, we knew almost nothing about the cosmos. We thought the stars were points of light fixed to a celestial sphere. We had no concept of galaxies or the Big Bang or the expansion of space. Now we have telescopes that can see light from the earliest epochs of cosmic history. We have theories that describe the evolution of the universe from its first moments to the present. We are actively pushing the boundaries of what is known. The Webb discoveries are a milestone in this ongoing adventure. They represent the cutting edge of human knowledge about the cosmos. They're also a reminder that there is so much more to learn. The surprises that Webb has found are surely not the last. Future observations will reveal more anomalies, more puzzles, more opportunities for discovery. Let me turn now to the future of cosmological research and what we might expect in the years and decades ahead. Webb is an extraordinary instrument, but it is not the only one. There's a whole ecosystem of telescopes and observatories working together to probe the secrets of the universe. I mentioned earlier that the Nancy Grace Roman Space Telescope is scheduled for launch in the coming years. This telescope will have a field of view 100 times larger than Hubble's, allowing it to survey enormous areas of the sky. While Webb excels at studying individual objects in exquisite detail, Roman will be a mapper, charting the positions and properties of millions of galaxies. Roman's surveys will help answer some of the questions raised by Webb. By studying the distribution of galaxies across cosmic time, it can test whether the impossible galaxies are common or rare. It can look for patterns in where these galaxies appear, what environments they inhabit, and how they relate to the cosmic web. Roman will also be a powerful tool for studying dark energy. By measuring the distances to many supernovae and the clustering of galaxies, it can probe the expansion history of the universe with unprecedented precision. This could reveal whether dark energy has been constant over time or whether it has changed, potentially connecting to the anomalies Webb has observed. On the ground, new observatories are coming online that will complement the space telescopes. The Vera C. Rubin Observatory in Chile will begin operations soon, conducting a survey of the entire southern sky every few nights for a decade. This repeated imaging will reveal changes in the universe, from exploding stars to moving asteroids to flickering quasars. It will generate a vast database that astronomers will mine for decades. The extremely large telescope, also in Chile, is currently under construction. When completed, it will have a primary mirror nearly 40 meters across, making it the largest optical telescope ever built. Its collecting area will dwarf anything that exists today, allowing it to see fainter objects and finer details than ever before. With such a powerful instrument, astronomers will be able to study the spectra of individual stars in distant galaxies. They will be able to resolve structures within galaxies that currently appear as blurs. They will be able to push the search for the first stars and the earliest galaxies to even greater distances. There are also radio telescopes that contribute to our understanding of the early universe. The Square Kilometre Array, an international project spread across Australia and South Africa, will be the largest radio telescope ever built. It will detect the faint radio signals from hydrogen gas in the early universe, revealing how this gas was distributed and how it fueled the formation of the first galaxies. One of the most exciting prospects is the detection of the 21-centimeter signal from the cosmic dark ages. Before the first stars formed, the universe was filled with neutral hydrogen that emitted a faint radio signal at a wavelength of 21 centimeters. By measuring the signal from different distances, astronomers can map the state of the universe before and during reionization. The 21-centimeter cosmology is still in its early stages. Current instruments have detected hints of the signal, but not yet the detailed maps that are needed to test our models. Future telescopes like the Square Kilometre Array should have the sensitivity to detect this signal clearly, opening a new window into the earliest epochs of cosmic history. Then there are the gravitational wave observatories. These instruments detect the ripples in space-time caused by the merger of massive objects like black holes and neutron stars. The LIGO and Virgo detectors have already made history by observing gravitational waves from dozens of events. Future gravitational wave observatories will be even more sensitive. The space-based LISA mission, planned for launch in the coming decades, will detect gravitational waves at lower frequencies than ground-based detectors can access. This will allow it to observe the mergers of supermassive black holes, the kind found at the centers of galaxies. If supermassive black holes were merging in the early universe, LISA might be able to detect the gravitational wave signals from those events. This would provide a completely different way of studying the growth of black holes, complementing the electromagnetic observations from Webb and other telescopes. All of these instruments together form a coordinated effort to understand the universe. No single telescope can answer all the questions. It takes a combination of different technologies, different wavelengths, and different approaches. The Webb observations are just one piece of a much larger puzzle that humanity is slowly assembling. Let me now return to the central mystery that has driven this exploration. What exactly did Webb detect that was so unbelievable? Let me be more specific about some of the most striking observations. One of the earliest results from Webb was the discovery of a galaxy called GLASZ-13. At the time of its discovery, it was a candidate for the most distant galaxy ever observed, with light emitted just about 300 million years after the Big Bang. Subsequent observations have refined our understanding of this galaxy and found others that might be even more distant. What makes GLASZ-13 remarkable is not just its distance, but its properties. It is compact but luminous, shining with the light of what appears to be billions of stars. For a galaxy existing so early in cosmic history, this level of activity is astounding. Our models predicted that galaxies at this epoch should be much smaller and fainter. Another stunning discovery involves a pair of galaxies known as the sparkler. These galaxies, observed behind a gravitational lens that magnifies their light, contain what appear to be globular clusters. Globular clusters are dense balls of ancient stars that orbit around galaxies. In the Milky Way, our globular clusters are among the oldest objects we know, with ages of 12 to 13 billion years. Finding globular clusters around galaxies in the early universe tells us that these clusters formed very quickly after the Big Bang. It also tells us that galaxy formation was already well underway because globular clusters typically form in the gas-rich environments of young galaxies. The sparkler is giving us a glimpse of what our own galaxy might have looked like in its youth. Webb has also observed some of the most distant quasars ever seen. Quasars are the luminous cores of galaxies powered by actively feeding supermassive black holes. They are among the brightest objects in the universe, visible across billions of light years. The most distant quasars tell us about the state of black holes and galaxies in the earliest times. One of the quasars Webb studied, known by the designation J1030+0524, hosts a black hole of about 1 billion solar masses. It existed when the universe was less than 700 million years old. How a black hole grew to such enormous size in such a short time remains a mystery. Webb's spectra of this quasar revealed interesting details about the gas around the black hole. The chemical composition of the gas, the way it was moving, the level of ionization, all of these provide clues about the environment in which the black hole grew. The data suggests that the region around the quasar was already chemically enriched, with significant amounts of heavy elements present. This is yet another sign that the early universe was more evolved than expected. Heavy elements take time to build up. They are produced by generations of stars living and dying. Finding them in such abundance so early means that intense star formation had already been happening for millions of years. The quasar observations also revealed outflows of gas being driven away from the black hole at high speeds. These outflows can carry heavy elements far from the galaxy, polluting the intergalactic medium. They can also regulate the growth of the galaxy by removing the fuel needed for star formation. Seeing such outflows in the earliest quasars tells us that the feedback processes that shape galaxy evolution were already operating. The interplay between black holes and their host galaxies, which continues to the present day, was already in progress less than 1 billion years after the Big Bang. There's another aspect of the Webb discoveries that deserves attention. The telescope has not only found surprising objects, but has also revealed the environments in which they exist. By mapping the distribution of galaxies in the early universe, Webb is showing us the structure of the cosmic web at that time. The cosmic web is the vast network of filaments and nodes that fills the universe. Galaxies form where the filaments intersect, at the densest points of the web. Between the filaments are voids, relatively empty regions where few galaxies are found. Webb has observed regions of the early universe where multiple galaxies are clustered together, potentially the precursors of the massive galaxy clusters we see today. These proto-clusters are interesting because they tell us about the growth of structure in the universe. The fact that they were already forming so early adds to the picture of rapid cosmic evolution. In some cases, Webb has found chains or streams of galaxies that appear to be connected, tracing the filaments of the cosmic web. This is consistent with our models, which predict that galaxies should form along these filaments. But the details of what Webb sees may require adjustments to our understanding of how matter was distributed in the early universe. Let me also mention the discoveries Webb has made about galaxies closer to home. While the telescope was designed primarily for studying the distant universe, it has also observed nearby galaxies in unprecedented detail. These observations provide context for understanding what we see at high redshift. By studying the stars and gas in nearby galaxies, astronomers can test the models they use to interpret distant observations. If a certain type of star or chemical signature is seen in a nearby galaxy, we can study it in detail and understand its properties. Then, when we see similar signatures in distant galaxies, we have a basis for interpretation. Webb has observed galaxies in the Local Group, the collection of galaxies that includes the Milky Way and Andromeda. It has studied the large and small Magellanic Clouds, satellite galaxies of the Milky Way that are visible in the southern sky. It has imaged star-forming regions, supernova remnants, and the centers of galaxies where black holes lurk. These local observations are not as dramatic as the discoveries in the distant universe, but they are equally important for building a complete picture of how galaxies work. Science advances by connecting the near and the far, the detailed and the general. Now let me address a question that might be on your mind. With all these surprising discoveries, is the standard model of cosmology in trouble? Should we be worried that our understanding of the universe is fundamentally wrong? The answer is complicated. The standard model, lambda, CDM, has been extraordinarily successful. It explains a vast range of observations, from the cosmic microwave background to the distribution of galaxies to the expansion rate of the universe. It is based on well-tested physics and has survived decades of scrutiny. The Webb observations do not overthrow this model. They do not show that the Big Bang did not happen or that the universe is not expanding. They do not contradict the existence of dark matter or dark energy. What they do is reveal details about the early universe that the model did not predict correctly. This is a sign that the model is incomplete, not that it is wrong. There is a difference. An incomplete model captures most of the truth but misses some details. A wrong model gets the fundamentals incorrect. Lambda CDM appears to be incomplete when it comes to describing the formation of the first galaxies and black holes. The task now is to figure out what is missing. Is it a small tweak, like adjusting the efficiency of star formation in the early universe? Or is it a larger revision, like modifying the properties of dark matter or the behavior of gravity? We do not know yet. It will take more observations and more theoretical work to find the answer. This is an exciting time to be studying cosmology. The field is in flux. Old assumptions are being questioned. New ideas are being explored. The next decade could see major breakthroughs in our understanding of the universe. Let me take you on a journey through time, from the Big Bang to the present, to put the Webb discoveries in context. Understanding where these impossible galaxies fit in the cosmic timeline helps appreciate why they are so surprising. The universe began about 13.8 billion years ago in an event we call the Big Bang. This was not an explosion in space, but an explosion of space itself. At the very beginning, all of space, time, matter, and energy were compressed into an unimaginably hot, dense state. In the first fraction of a second, the universe underwent a period of rapid expansion called inflation. During inflation, the universe grew by a factor of at least 10 to the 26th power, an almost inconceivable expansion. This inflation smoothed out the universe and seeded it with tiny density fluctuations that would later grow into galaxies and clusters. After inflation ended, the universe was still incredibly hot, filled with a plasma of subatomic particles. As it expanded and cooled, particles began to combine. Quarks formed protons and neutrons. Protons and neutrons formed atomic nuclei in a process called Big Bang nucleosynthesis. This happened in just the first few minutes and determined the abundances of hydrogen, helium, and a tiny bit of lithium. For the next 380,000 years, the universe remained too hot for atoms to form. Electrons could not stick to nuclei because the radiation was too intense. The universe was a glowing fog, opaque to light. Then came a moment called recombination. The universe had cooled enough for electrons to combine with nuclei and form neutral atoms. Light was suddenly able to travel freely through space. The glow that filled the universe at that moment has been traveling ever since, cooling and stretching. As the universe expanded, today we detect it as the cosmic microwave background radiation. After recombination came the cosmic dark ages. The universe was filled with hydrogen and helium gas, but there were no sources of light. No stars had yet formed. This era lasted perhaps 100 to 200 million years, though we do not know exactly how long. Then, somewhere in the darkness, the first stars began to shine. These primordial stars, called population 3 stars, formed from clouds of pure hydrogen and helium. They were likely massive and hot, burning fiercely and briefly. Their light began to ionize the surrounding gas, carving out bubbles of transparency in the foggy universe. This period, when the first stars and galaxies began to form and light up the cosmos, is called cosmic dawn. It was a transformative era, the end of the dark ages and the beginning of the structured universe we see today. Cosmic dawn is precisely the era that Webb was designed to observe. The telescope can see light from this period because it is sensitive to the infrared wavelengths that this ancient light has been redshifted into. Webb is our window into cosmic dawn. Following cosmic dawn came the epoch of reionization. The ultraviolet light from the first stars and galaxies gradually ionized all the hydrogen in the universe, transforming it from a neutral gas to an ionized plasma. This process was complete by about 1 billion years after the Big Bang. During this epoch, galaxies were growing and merging. The first supermassive black holes were forming. The chemical elements were being produced in stellar furnaces and spread through space by supernovae. The foundations were being laid for everything that would come later. From about 1 billion years to about 10 billion years after the Big Bang, the universe entered what is sometimes called cosmic noon. This was the peak era of star formation. Galaxies were producing stars at rates much higher than they do today. Massive bursts of star formation were common. The universe was actively building the structures we see around us. During cosmic noon, many of the galaxies we observe today were taking shape. Spiral arms developed, bars formed, galactic bulges grew, black holes at the centers of galaxies were actively feeding and growing. The interplay between star formation and black hole activity shaped the evolution of galaxies. After cosmic noon, star formation began to decline. The universe had used up much of the easily available gas. The remaining gas was harder to cool and harder to convert into stars. By about 10 billion years after the Big Bang, the cosmic star formation rate had dropped to a fraction of its peak value. Today, the universe is in a relatively quiet phase. Star formation continues, but at a much slower rate than in the past. Most galaxies are dominated by older stars. The expansion of the universe is accelerating due to dark energy, pushing galaxies apart faster and faster. This is the standard timeline of cosmic history, as understood before the Webb observations. It is a story of gradual evolution, of structures building up slowly over billions of years. The first galaxies were supposed to be small and chaotic. The first black holes were supposed to be modest in size. The heavy elements were supposed to accumulate. Gradually, what Webb found challenges this picture at the earliest times. The impossible galaxies appeared during cosmic dawn when things were supposed to be just getting started. They were massive and mature when they should have been small and primitive. The black holes were enormous when they should have been just beginning to grow. This does not change the later parts of the timeline. Cosmic noon still happened, the decline in star formation still occurred. The present-day universe is still what we observe. But the beginning of the story, the first few 100 million years, turns out to be different than we thought. It is as if we have been reading a book about the history of a city. The book describes how the city started as a small village and gradually grew over centuries into a metropolis. Then we discover old photographs showing that the city already had skyscrapers when it was supposed to be just a village. The rest of the book might still be accurate, but that first chapter needs to be rewritten. The rewriting of cosmic history is now underway. Scientists are working to figure out what really happened in those early times. They are developing new models, testing new theories, and gathering more data. The story of the universe is being revised in real time. Let me now talk about some of the human dimensions of these discoveries. Behind the data and the theories are real people, scientists who have dedicated their careers to understanding the cosmos. Their reactions to the Webb discoveries have been a mix of excitement, confusion, and determination. When the first impossible galaxies were found, there was a rush of activity in the astronomical community. Researchers who had been studying galaxy formation suddenly had to confront observations that contradicted their models. Some were skeptical at first, questioning whether the data could really be trusted. Others were thrilled, seeing an opportunity to learn something fundamentally new. The debates have been lively. Papers have been published arguing different interpretations. Conferences have been held where scientists present their findings and challenge each other. This is the normal process of science, messy and contentious, but ultimately productive. What is remarkable is how quickly the field has adapted. Within months of the first Webb observations, new theoretical models were being developed. Researchers who had never thought about the early universe before were jumping into the field. The pace of discovery has been exhilarating. I want to acknowledge the people who made Webb possible. The telescope is the product of decades of work by thousands of scientists, engineers, and technicians. It was proposed in the 1990s, developed through the 2000s, and launched in 2021. The journey from concept to reality took nearly 30 years. Along the way, there were setbacks and delays. The cost of the mission grew far beyond initial estimates. Technical challenges arose that seemed insurmountable. At several points, the project came close to being canceled. But the scientific community rallied behind it, convinced that the telescope would revolutionize our understanding of the universe. That faith has been vindicated. Webb is doing exactly what it was designed to do, and more. It is seeing things that no previous telescope could see. It is answering questions that have puzzled astronomers for decades. And it is raising new questions that will drive research for decades to come. The people who built Webb and operate it deserve enormous credit. They took a bold vision and made it real. They pushed the boundaries of what was technologically possible. They created an instrument that is transforming our knowledge of the cosmos. But the work is not finished. Webb is just the beginning. The discoveries it has made have opened new lines of inquiry that will require many telescopes and many years to follow up. The impossible galaxies are not the end of the story. They are the start of a new chapter. Let me now bring this exploration toward a conclusion by reflecting on what we have learned and what it means. We started with a simple statement. The James Webb Space Telescope detected something that no one would have believed if the telescope had not found it. What was that something? It was a universe that was already awake when it should have been asleep. It was galaxies that had already grown up when they should have been infants. It was black holes that had already become monsters when they should have been mere seeds. It was chemical elements that had already accumulated when they should have been scarce. In short, Webb found that the early universe was more active, more evolved, and more surprising than our models predicted. This is not a minor discrepancy. It is a fundamental challenge to our understanding of cosmic history. But challenges are good. Challenges drive progress. When our models fail to match observations, we learn that there is something new to discover. The impossible galaxies are telling us that there are processes in the early universe that we do not yet understand. Figuring out what those processes are will deepen our knowledge of the cosmos. Some possible explanations have already been proposed. Maybe the first stars were different than we thought, more massive and more efficient at producing light and heavy elements. Maybe black holes formed through unusual channels, skipping the normal stages of growth. Maybe dark matter played a more active role in sculpting the early universe. Maybe the expansion history was different than we assumed. Each of these possibilities is being investigated. More observations are being made. More theoretical work is being done. The scientific community is actively engaged in solving this puzzle. Within the next few years, we may have answers, or we may have even more surprises. What is certain is that our understanding of the universe has changed. The picture we had before Webb launched was incomplete. The picture we have now is more complex, more interesting, and more mysterious. We know more than we did, but we also know that we have more to learn. This is the nature of scientific progress. It is not a straight line from ignorance to knowledge. It is a winding path with unexpected turns. Sometimes we think we understand something, only to discover that we were missing a crucial piece. The journey never ends because there is always more to discover. The universe is vast beyond comprehension. It contains hundreds of billions of galaxies, each with hundreds of billions of stars. It has been evolving for nearly 14 billion years. The amount of information it contains is effectively infinite. No matter how much we learn, there will always be more. This might seem discouraging, but I find it inspiring. It means that the adventure of discovery will never be complete. There will always be new telescopes to build, new observations to make, new theories to develop. The frontier of knowledge stretches on forever. We are privileged to live at a time when we can participate in this adventure. A few generations ago, we did not have the tools to study the early universe. A few generations from now, they will have tools we cannot imagine. We are at a particular point in the journey, able to see farther than those before us, but not as far as those who will come after. The Webb discoveries are our contribution to the ongoing story. They are the gift we give to future generations, the foundation on which they will build. Just as we built on the discoveries of Hubble, Einstein, and others, future scientists will build on what Webb has revealed. Think about what it means that we can see light from 13 billion years ago. That light has been traveling through the expanding universe since before the Earth existed, since before the sun formed, since before the atoms in your body were assembled in dying stars. That light carries information about the earliest epochs of cosmic history, encoded in its wavelengths and intensity. And we can read that information. We have built instruments sensitive enough to detect those ancient photons and decode their messages. We have developed theories sophisticated enough to interpret what we see. We are reaching across almost the entire age of the universe to learn about Our origins, this is one of the most remarkable achievements of human civilization. We are a species that evolved on a small planet orbiting an ordinary star in an unremarkable corner of a typical galaxy. Yet we have developed the ability to understand the universe on the largest scales and the earliest times. We have become, in some sense, the universe understanding itself. The impossible galaxies that Webb found are part of this self-understanding. They are telling us that the universe is stranger and more wonderful than we knew. They are inviting us to revise our theories, to dig deeper, to learn more. They are a gift from the cosmos delivered by the most powerful telescope ever built. As I bring this to a close, I want to leave you with a sense of wonder. The universe is an amazing place. It is filled with mysteries waiting to be solved and marvels waiting to be discovered. Every time we think we have it figured out, something new appears to challenge us. The James Webb Space Telescope has opened a new window on the cosmos. Through that window, we are seeing things that reshape our understanding of how the universe began and evolved. The impossible galaxies, the early black holes, the mature structures in the infant cosmos, all of these are clues to a deeper reality that we are only beginning to grasp. We do not know where this journey will lead. We do not know what other surprises await us. But we know that the journey is worth taking. The quest to understand the universe is one of the noblest endeavors of the human spirit. It connects us to something larger than ourselves, to the vast sweep of cosmic history of which we are a small but significant part. So the next time you look up at the night sky, remember that you are seeing light from stars and galaxies that are unimaginably far away and unimaginably old. Remember that a telescope floating 1,000,000 miles from Earth is gathering that light and revealing secrets that were hidden for billions of years. Remember that we are part of this universe, made from its substance, shaped by its processes, and capable of understanding its story. The impossible has been detected. Now it is up to us to make sense of it. The adventure continues. If you have enjoyed this journey through the discoveries of the James Webb Space Telescope, please take a moment to like this video and subscribe to the channel. Your support helps us continue exploring the wonders of the cosmos together. Leave a comment below with your thoughts on what these discoveries mean for our understanding of the universe. We would love to hear from you. Until next time, keep looking up at the stars. The universe has so much more to show us. We now know that the universe began in a hot, dense state nearly 14 billion years ago. We know that it has been expanding and cooling ever since. We know that stars and galaxies form from primordial gas, and that the heavy elements in our bodies were forged in stellar furnaces. We know that life on Earth arose from this cosmic inheritance and that we are part of a larger story. This knowledge enriches our lives even if it does not solve practical problems. It gives us perspective, helping us see our troubles in the context of cosmic time. It inspires wonder, revealing a universe far more vast and strange than our ancestors could have imagined. It connects us to something larger than ourselves, a story that began before we existed and will continue long after we are gone. The impossible galaxies are the latest chapter in this story. They are showing us that the early universe was different than we thought, more active and more mature. This is not just an academic correction. It is a revision to our creation story, our understanding of how we came to be. There is also practical value in cosmological research, though it may not be immediately obvious. The technologies developed for astronomy often find applications in other fields. Detectors built for telescopes end up in medical imaging devices. Software written to analyze astronomical data is adapted for analyzing financial markets or genetic sequences. The skills and methods developed in pure research often turn out to be useful elsewhere. More broadly, investment in fundamental science drives innovation in ways that are hard to predict. The semiconductor revolution that made computers possible grew out of basic research in quantum mechanics. The internet began as a tool for physicists to share data. GPS relies on relativistic corrections that would never have been discovered without fundamental research into the nature of space and time. We cannot know in advance which discoveries will turn out to be practical. The safest strategy is to invest broadly in understanding the universe and trust that useful applications will follow. Cosmology is part of this investment, but even if cosmology never produced any practical benefits, I would still argue that it is worth doing. The human desire to understand is one of our noblest impulses. We are a curious species, driven to explore and explain. Satisfying that curiosity is valuable in itself, regardless of any practical payoff. The impossible galaxies satisfy our curiosity about the early universe. They reveal something we did not know and challenge us to understand it. That is enough justification for the research, even if nothing practical ever comes of it. Let me now tie together the threads of this exploration. We have covered a lot of ground, from the technology of the Webb telescope to the specific objects it has observed, from the theoretical models it is testing to the philosophical implications of what it has found. Let me summarize the key points. The James Webb Space Telescope is the most powerful astronomical observatory ever built. It sees infrared light with unprecedented sensitivity, allowing it to observe the oldest and most distant objects in the universe. It floats at the second Lagrange point, 1 million miles from Earth, shielded from the heat of the Sun, Earth, and Moon. When Webb began taking data, it found something unexpected. Galaxies in the early universe, from when the cosmos was only a few 100 million years old, were far more massive and mature than our models predicted. Some of these galaxies contained as many stars as the Milky Way does today. Some had spiral arms and bars, structures that were thought to take billions of years to form. These impossible galaxies challenge the standard model of cosmology, lambda CDM. This model has been incredibly successful at explaining the large-scale structure of the universe, but it appears to be incomplete when it comes to the earliest times. Something was happening in the first few 100 million years after the Big Bang that our models did not capture. Scientists are working to understand what that something is. Possible explanations include more efficient star formation in the early universe, unusual modes of black hole formation, modifications to our understanding of dark matter, and changes to the expansion history of the cosmos. More observations and more theoretical work are needed to determine which, if any, of these explanations is correct. Beyond the impossible galaxies, Webb has made many other discoveries. It has observed early supermassive black holes, protoclusters, barred spiral galaxies at high redshift, and evidence of chemical enrichment earlier than expected. All of these observations contribute to the emerging picture of a more active early universe. The implications of these discoveries extend beyond pure science. They touch on our understanding of where we came from and how we fit into the cosmic story. They remind us that the universe is more strange and more wonderful than we imagined. They challenge us to revise our theories and deepen our knowledge. The journey of discovery is ongoing. Webb has many more years of observations ahead of it. Other telescopes, both existing and planned, will add to what we learn. The impossible galaxies are not the end of the story, but the beginning of a new chapter. We live at a remarkable time. We have the tools to see almost back to the beginning of the universe. We have the theories to interpret what we see. We have the dedication and curiosity to keep pushing forward, even when the evidence challenges our assumptions. The universe has been around for nearly 14 billion years. Human civilization has existed for only a few thousand. Science as we know it has been practiced for only a few hundred. Yet in that short time, we have learned an astonishing amount about the cosmos, from the structure of atoms to the expansion of space to the evolution of galaxies. The Webb discoveries are the latest contribution to this growing body of knowledge. They are showing us that we still have much to learn. They are pointing us toward new frontiers of understanding. They are inviting us to continue the adventure that began when our ancestors first looked up at the stars and wondered, what will we discover next? We do not know. That is the beauty and the excitement of science. The universe keeps its secrets until we are clever enough to uncover them. The impossible galaxies were one such secret, hidden in the infrared glow of cosmic dawn, until Webb had the power to reveal them. There are surely more secrets waiting, more surprises that will challenge our assumptions and reshape our understanding. The universe is vast and old and strange, and we have only begun to explore it. I hope this journey has given you a sense of the magnitude of what the James Webb Space Telescope has achieved. It has not only confirmed some of what we expected, but has revealed things that no one predicted. In doing so, it has reminded us that the universe is more interesting than our theories, that reality always has more layers than our models can capture. The story of cosmic discovery is a human story. It is a story of curiosity and determination, of building tools to extend our senses and developing ideas to make sense of what we find. It is a story that includes ancient astronomers who mapped the stars with their naked eyes, Renaissance pioneers who first turned telescopes toward the heavens, and modern scientists who send machines into space to peer back in time. We are all part of this story. Every person who looks up at the night sky in wonder, every child who asks why the stars shine, every scientist who spends years analyzing data from distant galaxies, all of us are participants in the grand project of understanding the cosmos. The impossible galaxies that Webb found are the latest twist in this story. They have told us that the early universe was more awake, more active, and more evolved than we thought. They have shown us that our models need revision. They have opened new questions that will drive research for years to come. And they have reminded us that the universe still has the power to surprise us. No matter how much we learn, there is always more to discover. The frontier of knowledge stretches on without end. So let us continue the journey. Let us keep building telescopes, developing theories, and pushing the boundaries of what we know. Let us remain humble in the face of the vast unknown and curious about what it might contain. Let us be inspired by the impossible and determined to understand it. The James Webb Space Telescope has given us a gift, a window into the earliest moments of cosmic history. Through that window, we have seen wonders that no one expected. The impossible has become real. Now it is our task to make sense of it. Thank you for joining me on this exploration of what the James Webb Space Telescope has revealed. The universe is waiting with more secrets to share. Keep wondering, keep questioning, and keep looking up. If you found this journey through the cosmos worthwhile, please like the video and subscribe to the channel. Share your thoughts in the comments. What do you think these discoveries mean? How do you feel knowing that the early universe was more surprising than we imagined? We love hearing from our community. The universe is full of wonders. Let us explore them together. But there is one more dimension of the Webb discoveries that deserves our attention before we truly conclude. It involves the relationship between the impossible galaxies and the ultimate fate of the universe. What do these early cosmic surprises tell us about where everything is headed? The universe began in a state of extreme simplicity. In the first moments after the Big Bang, there was just a hot soup of particles, uniformly spread through space. Over billions of years, gravity sculpted this soup into the complex structures we see today. Stars, planets, galaxies, clusters, and the vast cosmic web all emerged from those humble beginnings. This process of structure formation is driven by gravity, which pulls matter together, and opposed by the expansion of space, which pushes things apart. The balance between these two forces determines how quickly and how thoroughly structures can form. In the current epoch, dark energy is winning. The expansion of the universe is accelerating, driven by this mysterious force that pervades all of space. Galaxies that are not already bound together by gravity are being pushed apart faster and faster. Given enough time, the universe will become increasingly empty and cold. But in the early universe, before dark energy became dominant, gravity had the upper hand. Matter was more densely packed, and structures could form relatively easily. This is why galaxies and clusters formed at all. If the universe had expanded too fast from the beginning, gravity would never have been able to pull matter together, and we would live in a featureless void. The impossible galaxies suggest that gravity was even more effective in the early universe than we thought. Structures formed faster and grew larger than our models predicted. This does not change the ultimate fate of the universe, which is still dominated by dark energy and accelerating expansion. But it does change our understanding of the journey from the Big Bang to now. If the early universe was more efficient at building structures, it means the cosmic story has more drama than we realized. The quiet, gradual assembly we imagined was actually a burst of activity, a frenzy of star formation and galaxy building in the first billion years. The universe was running at a faster pace before settling into the slower rhythm we observe today. This has implications for understanding the long-term evolution of galaxies. The objects we see nearby are the descendants of those early active systems. The Milky Way, Andromeda, and other local galaxies all have ancestors that were present in the early universe. If those ancestors were more massive and mature than we thought, it changes how we trace their lineage. Astronomers call this process galaxy archaeology. By studying the ages, chemical compositions, and motions of stars in nearby galaxies, they try to reconstruct what those galaxies looked like in the past. The Webb observations are providing direct evidence about the early stages, allowing astronomers to check their archaeological reconstructions against actual observations of ancient systems. The match is not always good. Some galaxies appear to have formed more rapidly than the archaeological evidence suggested. This is prompting revisions to the models used for reconstruction. Once again, Webb is forcing us to update our understanding. Another aspect of the long-term evolution involves the growth of supermassive black holes. These objects sit at the centers of galaxies and can have profound effects on their hosts. When a black hole actively feeds, it releases enormous amounts of energy that can heat and expel gas, suppressing star formation. When it is quiescent, gas can cool and form stars more freely. The feedback between black holes and galaxies is thought to regulate their growth, keeping black holes and galaxies in a rough proportion to each other. This relationship, called the black hole-galaxy mass relation, has been observed in the nearby universe. Bigger galaxies tend to have bigger black holes. Webb's discovery of massive black holes in the early universe raises questions about when and how this relationship was established. If black holes were already enormous when their host galaxies were young, it suggests the relationship was in place from the start. Alternatively, the early black holes might have been unusually large relative to their galaxies, with the balance being restored later through galaxy growth. Disentangling these possibilities requires detailed observations of many systems across cosmic time. Webb is providing essential data for this project, but it is only one piece. Ground-based telescopes, radio observatories, and future space missions will all contribute. Let me also discuss how the Webb discoveries relate to the search for extraterrestrial life. This might seem like a jump from cosmology to astrobiology, but the connections are real. Life as we know it requires certain conditions. It needs a stable energy source like a star. It needs planets with the right temperatures and chemical compositions. It needs time for complex chemistry to develop into biology. All of these requirements depend on the cosmic context. If the early universe was more active than we thought, it means stars and heavy elements appeared earlier and in greater abundance. This could have created habitable environments sooner. The window of time during which life could potentially arise would be longer. Of course, having habitable environments does not guarantee that life will arise. We still do not understand how life originated on Earth, let alone whether similar processes could happen elsewhere. But expanding the window of opportunity makes it more likely that somewhere in the vast universe, conditions were right. The impossible galaxies are telling us that the universe was ready for complexity earlier than we assumed. Whether any of that complexity included life is a question we cannot yet answer. But Webb is helping to frame the question more precisely. Webb is also directly searching for signs of habitability around other stars. By analyzing the atmospheres of exoplanets, it can look for molecules that might indicate biological activity. Water vapor, carbon dioxide, and methane are all detectable with Webb's instruments. If these molecules appear in certain combinations, it could hint at the presence of life. So far, no definitive biosignatures have been found. The search is incredibly difficult because the signals are faint and the interpretations are ambiguous. But every observation brings us closer to answering one of humanity's oldest questions. Are we alone? The connection to the impossible galaxies is philosophical as much as scientific. Both discoveries remind us that the universe is full of surprises. Both challenge our assumptions and expand our sense of what is possible. Both invite us to imagine a cosmos richer and more diverse than our models suggest. Whether life exists elsewhere in the universe is a mystery that may take generations to solve. Whether the early cosmos was more active than our models predict is a question we are answering right now thanks to Webb. These mysteries are related threads in the larger tapestry of cosmic understanding. Let me now address a topic that often comes up when discussing major scientific discoveries. It concerns the role of uncertainty and how we should think about tentative results. The impossible galaxies are real observations. The data from Webb is solid. But the interpretation of that data involves assumptions and models that could be wrong. When scientists say these galaxies challenge our theories, they are acknowledging that either the observations have been misinterpreted or the theories need revision. It takes time to figure out which. This uncertainty is not a weakness of science, but a feature. scientists are honest about what they do not know. They present their results with appropriate caveats, acknowledging the limits of their data and methods. This honesty is what makes science trustworthy in the long run. When you hear about scientific discoveries in the news, it is worth remembering that the details often change as more evidence comes in. The initial reports about the impossible galaxies were exciting but preliminary. Since then, more observations have been made, more analyses have been performed, and the picture has become both clearer and more complex. Some of the earliest claims about impossibly massive galaxies have been revised. More careful analysis of the data suggests that some galaxies might not be quite as massive as first thought, but others have held up to scrutiny and remain genuinely puzzling. The overall message that the early universe was more active than expected remains valid even as the specifics evolve. This is how science works. Initial discoveries are followed by refinement and sometimes revision. The path to truth is not straight but winding. Patience and persistence are required. The final answer, if there is one, emerges gradually from many contributions. The Webb observations will continue to be analyzed and debated for years. New data will be collected, new theories will be proposed. Eventually, a consensus will emerge about what the impossible galaxies tell us about the early universe. But that consensus will itself be provisional, subject to revision if new evidence demands it. This is the humility of science. We do not claim to have absolute truth. We claim to have the best current approximation, always open to improvement. The impossible galaxies are an invitation to improve our approximation, to bring our models closer to reality. Let me bring this extended exploration to a close by reflecting on the human dimension once more. The James Webb Space Telescope represents one of humanity's greatest technological achievements. It is a machine of astonishing complexity, built to withstand the harsh environment of space and perform observations of incredible precision. But behind the machine are people. Thousands of scientists, engineers, technicians, and administrators worked for decades to make Webb a reality. They faced setbacks and delays, budget crises, and technical failures. They persevered because they believed in the mission, in the importance of understanding the universe. These people come from countries around the world. Webb is an international project, a collaboration among space agencies and research institutions, spanning continents. It is a testament to what humanity can achieve when we work together toward a common goal. The discoveries Webb is making are the fruit of that collaboration. When we see images of distant galaxies or learn about the chemical composition of exoplanet atmospheres, we are seeing the culmination of decades of human effort. Every pixel in those images represents countless hours of work by people whose names we may never know. Science is a collective enterprise. No single person could build a telescope like Webb or interpret its observations alone. It takes communities of researchers, each contributing their expertise to make sense of the universe. The impossible galaxies were discovered not by one genius, but by teams of scientists working together. This collaborative spirit is one of the most admirable aspects of modern science. Researchers share their data, publish their methods, and invite others to check their work. When mistakes are found, they are corrected. When credit is due, it is acknowledged. The pursuit of truth is a communal endeavor. As you go about your daily life, the universe continues its ancient rhythms. Stars are being born in distant nebulae. Galaxies are colliding and merging. Black holes are swallowing matter and growing larger. The cosmic web is evolving, with filaments stretching and voids expanding. And somewhere, in a region of space we have not yet observed, there may be more impossible objects waiting to be discovered, more surprises that will challenge our theories and expand our understanding. The universe is not finished surprising us. The James Webb Space Telescope has opened our eyes to a cosmos more strange and wonderful than we imagined. The impossible galaxies it found are just the beginning. What comes next is unknown, and that is precisely what makes it exciting. We are explorers of the cosmos, using our machines and our minds to push back the darkness of ignorance. Each discovery is a small victory, a step forward on an endless journey. The impossible galaxies are one such step, and there are many more to come. Thank you for staying with me through this long exploration. The universe rewards patience and curiosity. May you always find wonder in the night sky and joy in the quest for understanding. The cosmos is vast, The journey is long and the adventure is just beginning. Until next time, keep looking up. The stars are waiting. There is something deeply moving about contemplating the vast reaches of space and time. When we look at images from the James Webb Space Telescope, we are seeing light that has traveled for billions of years. That light left its source when the universe was young, when Earth did not yet exist, when the atoms that would eventually become you and me were still scattered through interstellar space. The photons that Webb collects have witnessed the entire history of cosmic evolution. They passed through the expanding universe, redshifting as space stretched around them. They traveled through voids and past galaxies, through regions where stars were being born, and others where stars had already died. They crossed distances so vast that our minds struggle to comprehend them. And then, after all that time and distance, those photons were gathered by a mirror floating 1,000,000 miles from Earth. They were focused onto detectors, cooled to near absolute zero. They were converted into digital signals and transmitted back to our planet. They were processed by computers and analyzed by scientists, and finally, they became images that you and I can look at. Windows into a past so remote it defies imagination. This chain of events, from the emission of light in a distant galaxy to its reception on Earth billions of years later, is one of the most remarkable things about astronomy. We are not just observing the universe, we are participating in a cosmic communication, receiving messages sent before humanity existed. The impossible galaxies are messages from the dawn of time. They are telling us that the universe was more alive in its youth than we expected. They are challenging us to revise our understanding of cosmic history. They are inviting us to think bigger, to imagine processes and phenomena that our current theories do not capture. Responding to this invitation is the work of science. Researchers around the world are poring over the Webb data, looking for patterns and anomalies. Theorists are developing new models to explain the observations. Students are being trained in the techniques needed to push the frontier further. The enterprise of cosmic exploration continues. And it is not just professionals who participate. Anyone with curiosity can follow along. The images from Webb are publicly released. The scientific papers are freely available. The discussions and debates take place in public forums. You do not need a degree in astrophysics to appreciate what is being discovered. You just need wonder. Wonder is the starting point of all science. It is the feeling that arises when we confront something unexpected, something that does not fit our existing framework. The impossible galaxies evoke wonder because they challenge what we thought we knew. They open a gap between expectation and reality, and that gap is where discovery lives. I hope that this exploration has kindled some wonder in you. The universe is filled with marvels, and the James Webb Space Telescope is revealing them at an unprecedented pace. The impossible galaxies are just one example. There will be many more in the years ahead. Let me leave you with some thoughts about how to engage with these discoveries. You do not have to understand every technical detail to appreciate the significance of what is being found. The basic story is accessible to everyone. The early universe was different than we thought. Our models need revision. There is more to learn. If you want to go deeper, there are excellent resources available. Websites like NASA's Webb portal provide regular updates on new discoveries. Popular science magazines and websites cover the latest findings in accessible language. YouTube channels dedicated to astronomy explain complex topics with visuals and analogies. There is no shortage of ways to stay informed. You can also contribute to science directly through citizen science projects. Some astronomical research involves analyzing large datasets that benefit from many eyes. Projects like Galaxy Zoo invite members of the public to help classify galaxies based on their shapes. This kind of collective effort has led to real discoveries and demonstrates that science is not just for professionals. And of course, you can simply look up at the night sky. The same stars and galaxies that Webb observes are visible from your backyard, though much fainter and without the detail that the telescope provides. There is something profound about connecting your direct experience of the sky with the knowledge gained through advanced instruments. The universe belongs to all of us. It is our common heritage, the context in which our existence unfolds. Understanding it better is not just the province of scientists. It is a human endeavor that enriches everyone who participates. The impossible galaxies are a reminder that our understanding is always provisional. What we think we know today may be revised tomorrow. This is not a reason for cynicism, but for excitement. Every revision is an opportunity to learn something new. Every challenge to existing theories is a doorway to deeper truth. The scientific community is energized by the Webb discoveries. Researchers who have spent their careers studying galaxy formation suddenly have new puzzles to solve. Young scientists are entering the field, drawn by the excitement of working with revolutionary data. The pace of publication is accelerating as teams race to make sense of what Webb is showing us. This ferment of activity is science at its best. The established order is being questioned. New ideas are being proposed. Data is being analyzed and reanalyzed. Debates are being held at conferences and in journal pages. Out of this productive chaos will emerge a new understanding, more accurate and more comprehensive than what came before. Or we do not know yet what that new understanding will look like. The impossible galaxies might require only minor adjustments to existing models, or they might demand a more radical rethinking of cosmic history. The answer will come from the interplay of observation and theory, data and interpretation, imagination and rigor. What we do know is that the universe continues to surprise us. Every generation of astronomers has encountered phenomena that their predecessors did not anticipate. The expansion of the universe, the cosmic microwave background, dark matter, dark energy, gravitational waves, all of these were surprises in their time. The impossible galaxies are the surprise of our time. Future generations will have their own surprises. They will have telescopes more powerful than Webb, theories more sophisticated than ours, and questions we have not yet thought to ask. They will look back on our era as we look back on Hubble's, appreciating our contributions while recognizing our limitations. This is the nature of scientific progress. Each generation builds on the work of the previous one, advancing the frontier of knowledge a little further. We are part of a chain that stretches back to the first humans who wondered about the stars, and forward to descendants we will never meet. The impossible galaxies are our contribution to this chain. They are the mystery we have uncovered, the challenge we leave for those who come after. Solving it will require creativity, persistence, and collaboration. The tools exist, the talent exists, the will exists. The only question is time. And time, in cosmic terms, is something we have plenty of. The universe has been around for nearly 14 billion years and will continue for trillions more. The stars will keep shining, the galaxies will keep evolving. The great cosmic drama will unfold regardless of whether we are watching. But we are watching. That is our unique gift and responsibility. We are the part of the universe that has become aware of itself, that asks questions about its own nature, that seeks to understand the forces and processes that shaped it. The impossible galaxies are a test of that understanding, a puzzle that the universe has set for us to solve. We will solve it. Maybe not today, maybe not tomorrow, but eventually. That is what science does. It takes the unknown and makes it known. It takes the impossible and makes it explicable. It takes the wonder of discovery and transforms it into the satisfaction of understanding. Until then, we watch and we wait and we wonder. We gather more data, we refine our theories. We debate and discuss and disagree. And through it all, we remain committed to the pursuit of truth, however strange or surprising that truth may turn out to be. The James Webb Space Telescope has shown us something we did not expect to see. Galaxies that were too big, too bright, too mature for their age, black holes that grew too fast. A universe that was already awake when it should have been sleeping. If Webb had not detected this, no one would have believed it. But Webb did detect it, and now we must believe it. The universe is stranger than we knew. Our models are incomplete. There is work to be done. Let the work continue. Let the discovery go on. Let the wonder never fade. The cosmos is calling, and we are listening. Thank you for being part of this journey. Your curiosity and engagement are what make these explorations worthwhile. If you enjoyed this deep dive into the Webb discoveries, please support the channel by liking the video and subscribing. Leave a comment with your thoughts. Share this with someone who might find it interesting. The universe has so much more to show us. Stay curious, stay wondering, stay connected to the cosmos that made you. Until we meet again under the starlit sky, the night sky holds more secrets than we have ever imagined. Every point of light is a story waiting to be told. Every galaxy is a history waiting to be read. The James Webb Space Telescope is teaching us to read those histories in ways we never could before. What awaits in the uncharted depths of cosmic time? What other impossible things will we find? The answer lies in the infrared glow of ancient starlight, in the data streaming down from a telescope floating beyond the moon, in the collective effort of humanity to understand its place in the grand tapestry of existence. The impossible has been found. Now comes the harder part, making sense of it. That is the work of generations. That is the gift we give to the future. That is the endless, wonderful adventure of science. Keep watching the sky. The universe is always ready to surprise you. The stars remember everything. Now, so do we. That is the power of discovery. That is what makes us human. That is why we look up.